Okay, welcome back, and we'll continue now with Yuri Kovchegov's going to tell us. This is the first of two lectures on QCD, small x, and saturation. So, Yuri, welcome.
Thank you very much. Thanks for the organizers for putting the scope together. So I'll talk about small x physics and saturation, and I've been debating for a long time with myself whether to do it slides only or to do some of it on the blackboard. Slides only, of course, will be very fast. I'll cover a lot, though, but if I do it on the blackboard, I'll uncover a little. So I'll cover less, but at a slower pace. So what do you guys feel like? Blackboard? Blackboard? For sure. Yeah? Okay, excellent. Very good. So, glad you heard the verdict. So I'm gonna, since it's a Blackboard lectures, there are slides, by the way, posted. You can read them later or even in parallel to my discussion. But we only have 2 hours, right? An hour today, an hour tomorrow. So it will be fairly. I have to pick a specific topic. Physics of small x physics is fairly large. Physics of saturation is fairly large. There are many observables, but I will pick a specific observable that I'll talk about and analyze it from the small x perspective, not from the maybe perturbative QCD perspective that you've seen last week and earlier today. And then I have no time, but I'll just point you to ways of analyzing other observables in a similar way. So if it's a Blackboard, then let's, sorry, you have to turn your chairs or desks and whatnot. Let's turn your heads. So the first topic, so small x and saturation is the big topic. And first, we're going to talk about deep and elastic scattering. There is no. So, and electron proton scattering, deep elastic scattering specifically is what I'll talk about for the 2 lectures we'll have. Like I said, I have to pick a process, and that's what our process will be. So let's start with some general information, which I'm sure all of you know. And by the way, please feel free to interrupt me if I'm saying something that's not clear, or in general to ask the question. So I want this to be fairly interactive as much as time allows. And also, if you feel like I'm repeating something you've seen many, many times. Oh, is this too low in the back there? No, they're not movable. I'm sorry. I cannot cut below halfway. I'll try to write things on top, but it's maybe if you could just slide closer somewhere, that might be a better solution. Okay, so this picture you've seen before. We have, say, an electron come in, and we have a proton down here. Proton has momentum p. Electron exchanges a virtual photon with one of the quarks in a proton and breaks up the proton. Right before the interaction, the proton was nice, coherent, bound state. Electron comes in, packs the proton with a photon, knocks out at least one of the quarks out of the photon, and usually this is some stuff, right? These are remains of the proton which hadronize, produce hadrons that we measure in a detector. Electron by itself bounces off, so we usually put some incoming momentum k, outgoing k prime. The proton has momentum p, the photon has momentum q, let's say the struck quark has momentum L in a proton, and after the interaction, it has momentum L plus Q, right? How many of you have not seen this picture of deep elastic scattering? Okay, so everyone has seen it, done it. So you know there are variables we define photon virtuality Q squared, which is negative 4 vector Q squared. It's always positive. That means that the virtual photon is always space-like, right? We have center of mass energy of the photon-proton system. So this is a proton plus gamma star CMS energy squared. Right, so oftentimes we factor out the electron part and we think of this interaction with the photon interacting with the proton because all the strong interactions which interest us are happening down here, right? The photon electron photon vertex is a QED vertex. You've seen it, done it, right? This is just basic 3-level ENM QED calculations you've done in your field theory class many times. And another variable is a Bjorken X variable. Which is defined as q squared over 2p dot q. And you can also rewrite this in terms of w squared as q squared divided by w squared plus q squared minus the proton mass squared. Okay. So we have x and q squared. These are the variables we'll work with most of the time. MP, like I said, is the proton mass. Okay. Now you can see that if we're interested in high energy scattering, high energy means omega squared is large. So high energy, omega squared is much bigger than q squared. That means what happens to x? Small, right? If omega squared is much bigger than q squared and say much bigger than mp squared as well, then x is small. So high energy physics is small x physics, right? So when we say small x, it doesn't mean that our ambition is small. It means that we're actually interested in high energy, right? We want to understand how QCD is at high energies. Okay, that's a goal. Kinematics. So we use the light cone variables. We have V plus minus, which would be V naught plus minus V3 over root 2 for any vector V mu. How many of you have not seen plus and minus variables? Maybe sometimes they're defined without. So everyone has seen variables? No. Okay, somebody there did not. So it's just a variable change. If you wish, it's a rotation in a space-time plane. So if this is, say, time axis, this is the z-axis. We define the variables. One is the sum of the two divided by root 2. One is the difference. So we're just kind of rotating the axis. And we define an x plus variable and x minus variable this way. Okay. For vector, I'm gonna write here. So for vector squared, which you usually write as v naught squared minus 3 vector v squared, is actually can be written as 2v plus v minus minus v perp squared, where by v perp I mean that two components which are in the transverse direction. So it's a notation which is very convenient for high energy collisions. We have a special axis, the z-axis, along which the particles collide. Say if we're going to be working in a frame now where the proton comes along and moves along the positive z direction, the virtual photon comes and moves along the negative z direction. So actually they will be moving along these two light cones. The proton will be moving along the x plus light cone. The photon will be moving along the x minus light cone. And these transverse components are two-dimensional transfers to the direction to the z-axis, right, in space. I cannot draw you a full 4-dimensional diagram on a 2-dimensional blackboard, but I can wave my hands a lot, and hopefully that helps. Okay, so parts of it. All right, we use this plus notation, like I just said. The proton is moving, so the proton is here. is gonna come along the light cone, and the virtual photon is gonna come along the other light cone. So we imagine high energy scattering. The proton's momentum for momentum is it has a big P plus, it has no transverse momentum, and it has a minus component as well. So this is a plus minus term notation. For the virtual photon, we're going to have negative q squared over 2 q minus 0 in terms of momentum as well. So p plus and q minus are large. The way I'm writing these things, you can, I think, try to go too far to the right. You just require that 4 vector squared for the proton is equal to mp squared. If p curve is 0, right? So this is say 2p plus p minus minus p curve squared. If p curve is chosen to be 0 by the frame, we can see right away that we can solve this for p minus as mp squared over 2p plus, right? So that's how this came about. And similarly, this component came from the condition that little q squared is equal to negative big q squared. So q squared is sort of like a mass of the photon, except it comes with the wrong sign. So the photon has an imaginary mass of iq, right? And that's why here is plus mp squared, here is minus q squared. Okay, so this was the proton. And this is the photon. Okay. So let's do a little bit of a calculation. You just look at this diagram and you say, oh, okay, my quark here is in a final state. It is produced, right? It's an on mass shell quark. So that immediately tells us something. Let's just put it this way. So we have L plus Q squared. Let's make it equal to 0. So massless, I'm going to assume that quarks are massless, and this outgoing quark is on mass shell. This is the statement here. So we open the parentheses, L squared plus 2 L dot Q plus Q squared. All of this is equal to 0. This is equal to L squared plus 2 L dot Q minus capital Q squared. Usually you say, all right, the quark is moving mainly in the direction of the proton. Quark inside the proton is moving in the proton direction, more or less collinear. So L plus momentum, just like the proton has a big P plus momentum, L plus momentum is large. So I'm going to assume that L plus is large. Then we approximate this dot product as L plus Q minus. And we can neglect L squared compared to it. And remember, all of this is equal to 0. So we get L plus is equal to Q squared over 2Q minus, right? Equivalently, L plus over P plus, the fraction of the proton's plus momentum carried by the quark, is equal to Q squared over 2P plus Q minus. Does anyone know what this 2P plus Q minus is in terms of the variables I have defined on this side of the board? W squared, somebody said, right? Right, so this is approximately W squared, because W squared, remember, is P plus Q squared. You open the parentheses, you get MP squared from P squared, you get negative Q squared from little q squared, and then you get 2P dot Q. And if you take a dot product of these two guys, oh, I'm sorry, I forgot to write, maybe it's instructive for those of you who have not seen light cone notation. This is the square over 4 vector in light cone coordinates. If you have two different 4 vectors multiplying each other, you're going to get U plus V minus plus U minus V plus minus U curve dotted into V term. And I'm leaving this out. I have no time to spell it out, but you can just plug in the definitions of light coordinates and convince yourself that this is indeed the standard four vector product as you've seen it in your special relativity class, E&M class, whatever you see in special. Is it okay to leave it like this? Okay. So the dot product of P dot Q then is gonna have P plus multiplying Q minus, and those are both large, plus other terms which are small. So we see that this W squared with high energies is 2P plus Q minus. Okay. So so this is Q squared over W squared. We can also write this Q squared over 2P dot Q, which is X Bjorken. Right? So we see that right away, something you have seen before. Well, yeah, we see that I ran out of the blackboard, that's what we see. But let me summarize it up here, that X is equal to L plus over P plus. So Bjorken X was defined here as a kinematic variable, Lorentz invariant kinematic variable. On the other hand, in the frame we're working in, it has the meaning of the fraction of the proton momentum carried by the struck quark. Okay, so maybe I should make myself some room here and write this down. So this is, I'm just moving L plus large down here. X has a meaning, so fraction of proton momentum carried by quark, by the struck. Okay, so in high energy scattering, right? Maybe somewhat paradoxically, remember we said when energy is high, X is small. When X is small, that means that this quark carries a very small fraction of the proton momentum, right? So in high energy scattering, we're probing the quarks which carry the least amount of the proton light momentum. Okay, so that's one of the things we learn from here. Any questions? I know it is still a bit rushed, even though it's Blackboard, but we only have 2 hours to cover it on this material. But it's okay to ask questions. No? Seen it, done it? Okay, then let's move on. Well, next, what do we do? To calculate the cross-section, we square this diagram. So let me not completely erase them and just square it up here on top to show you something you also, most of you must have seen. So squaring the diagram, we get something like this. This is our electron line, this is the photon line, the quark line. This is the proton. And then we have all this here, and this is the final state count, right? So this is the virtual photon, this is the proton, again a virtual photon, this is the electron, and that's pretty much it. So you see right away that the process factors into 2 pieces, and I alluded to those before. You have the leptonic tensor, say L mu, and you have the hadronic tensor W mu. Right? L mu is just made out of these electron photon vertices. It's just a QED process. Like I said, we can all calculate it in 5 minutes. W mu, well, no one can calculate, period, right? From just principles, QCD. So the cross section, the sigma E3 K prime, where K prime, remember, was the momentum of the outgoing electron, is equal to all the NM squared over Q squared E prime. These are energies of the incoming and outgoing electron. L mu, W mu. And this is written in a rest frame. So in proton rest frame. I'm not deriving this, but I presume that you have either seen it before or can derive it yourselves. This is just a two particle scattering. Two particle scattering into electron and black. And we can write down just cross sections using the usual standard QFT rules. So L mu, like I said, is the lepton tensor. And that's easy. Calculate. The hard part is the hadronic tensor. Which is W mu. So there's a prefactor, that's a convention, 1/4 pi mass of the proton, integral d for x into the I q dot x. Does anyone know what else to write here?
D Ra
Okay, Ra, D. Okay, the proton state, very good.
and
No,
current.
answer- no.
the current.
Current. The current, what current? The electromagnetic current, right? The weak current with the axial current, right? It's just a vector current. Maybe another one? What do you say?
Think another one.
Yes, another one. The mu and the proton state. Okay, very good. So many of you have seen this and have worked with it. So this is a hadronic tensor, right? We have two indices, let's say mu and nu. Let's work in the gauge where like Feynman gauge for the photon propagator. So when you have one Lorentz index on each, if you wish. So we have index mu. This is the insertion of J mu current. This is the insertion of J nu current. And today I'm talking about spin averaged observables. So there's no proton spin here. I know you have lectures on the last week. So J mu of x is the electromagnetic current. Okay, so far so good. All right, so this is just general knowledge, nothing specific to small x so far. Though I did talk about kind of being in a frame, in the infinite momentum frame where the proton is moving along the light cone. Let's now, well, I'm going to redraw this picture that I'm erasing. Let's now evaluate W mu, or try to evaluate W mu in high energy scattering, right? So maybe I shouldn't have erased these. Let's leave them. Like this. Everything else, I guess we can use. So, like I mentioned before, W mu is the hadronic tensor. That's where the interactions, the strong interactions are. And that's what we are interested in understanding. And suppose we want to calculate it at high energies with this P mu and Q mu, right? Well, P mu we don't care so much just yet. Let's first look at Q mu, which is explicitly here in the Fourier transform, right? So e to the I q dot x in our frame where Q has no per component. So let's just do it slower for those of you who have not seen light cone notation before. Right, so this is just a dot product of two Fourier vectors, Q and X, in light cone coordinates. Now, in our frame, Q perp is 0, and Q plus is negative Q squared over 2Q minus. So we get e to the I Q minus X plus minus Q squared over 2Q minus minus. Okay. Say, all right, very good, but what does it all mean? Well, what it means is, okay, let's go back to W mu, and by the way, if my mu and nu are upper on the right-hand side, this should have been up on the left-hand side for those of you who want the indices to be correct. Apart from this, we have this exponent, e to the I q minus x plus minus q squared over 2q minus x minus the proton state j mu of x, j mu of 0 to proton state. Okay. I haven't done anything. I just rewrote the hadronic tensor in this frame where the photon is moving with large momentum along the light cone, along the minus. Okay. So we know that Q minus is large. Let's even say very large. Okay. If Q minus is very large, by uncertainty principle, what happens to X plus? Small, right? So X plus is small. That means the two currents are separated by very little distance in X plus direction. What about X minus? When I say that Q minus is large, I really mean it. It's larger than Q squared, right? So Q minus is also much larger than Q squared, than Q, right? Remember, we're in the high energy regime where center of mass energy is larger than Q squared. Really, in high energy QCD, we're not at OK energy where Q squared is a large scale. I mean, Q squared still could be much larger than the QCD scale. It could be a perturbative scale, but Q minus is still much larger. So what do you say about X minus? Large. Yeah, X minus could be large. So X plus is small. X minus will be, by uncertainty principle, right? Just the inverse of this coefficient of the order of 2Q minus over Q squared. And this is potentially large. Okay. So what does it mean, right? So now I want to picture this W mu in a space-time notation. Now the experts in the room are going to pick on me, and they will be right. They would say that this is not a time-ordered product, that it's just a product of two currents. I cannot write it as in space-time. This is all correct, but usually one fixes it by defining T mu, which is the same thing as W mu, but with a time-ordered product of the two currents. And the time ordering, remember, time ordering means that you're within the same amplitude, right? You can use Feynman rules. If you have just a product of two operators, it's like an amplitude squared for these two local operators. But anyway, these are all technical details. So I can define T mu and argue that it's twice imaginary part of the thing IW mu. Don't quote me on this file, but one can define a related quantity and bypass all the technical details. But nonetheless, let's imagine this process with W mu or T mu in space-time. So again, we have a proton which is ultra-relativistic. And like I said, it's moving in the light cone X plus direction, right? So it's just moving practically with the speed of light in the positive Z direction. Okay. Now we have these two currents. So one is one current here is chosen at 0. This doesn't mean that it has to always be at the origin. This is just using people use translational invariance of the momentum eigenstates, which are p states, to shift this to 0. Right? In reality, I can choose this to be any variable y mu, the argument of the current, and this one will be any variable, I don't know, z mu, as long as z mu minus y mu is x mu. That's up, right? I have complete translation invariance. So nobody tells me that the current has to be at the origin where I drew the origin. This is just a random point, right? Again, P is a state of the proton, but it's a momentum state of the proton. So the proton has no specific position. So anyway, we choose a position there, but the current can be anywhere with respect to the proton. However, the point I'm trying to make is that these two currents are separated by X minus, which is very very large. So the proton is moving along the light cone. It's Lorentz contracted already, right? The proton has a radius of about what 0.84, 0.86 Fermi in its rest frame. If you boost it, it's Lorentz contracted. Here comes a virtual photon, and it has to become current. That means it has to have this vertex somewhere, and then it has another vertex down here, and the x minus time between these two vertices can be large. In fact, it could be much larger than the proton size. So what I'm trying to draw, let me draw the answer, and then you'll see what I'm trying to say is that this vertex of a photon's coupling to the quark and antiquark does not happen inside the proton. Most of the time, this x minus distance is much larger than the proton, right? So if you have a photon vertex, QQ bar vertex, or photon quark vertex here and here, most of the time they are outside the proton. We just, right? So this distance between these two guys is this x minus here. And if it's very, very long, it's much bigger than the proton size. And most of the time, the splitting and mergers happen outside of the proton, right? So that's a very different picture from what that handbag diagram on the left that you have seen before suggests, right? In the handbag diagram, you can imagine that the photon comes in and interacts with the proton, and the proton immediately spits out the photon. Well, at high energies, this is not how it happens. At high energies, the dominant contribution is this quark-antiquark pair interacting with the proton. Okay, so we still have a separation of a QED process, photon splitting into QQ bar pair emerging back into a photon. That's all very good. But the strong interaction now is not this knockout process where the photon knocks out the quark out of the proton. We have a quark-antiquark pair, a dipole, if you wish. I'm going to be using that term relatively frequently. We have a quark and antiquark, which came from the photon. That means their colors are equal and opposite to each other. So the color singlet state of a quark and antiquark, which plows through the proton and interacts with it. Okay, so it's a different paradigm. It's a different issue. We're not going to be looking at this again knockout process. We have a quark-antiquark dipole interacting with the proton. Okay, questions? Everybody agrees. No one has any objections. Yeah.
This quartz corresponds to the quartz of zero payment diagram there, or they are?
Well, quarks are quarks. Quarks are all equivalent, but you can think of it. So one way of thinking about it, where is the eraser? One way of maybe, so the answer is the same principle, quark and antiquark, but you can kind of think of, so suppose you take this photon and you start pulling on it, and you pull the quark and antiquark out of this blob, if you wish, right? So you kind of distort this picture into something like that. And you do the same thing on the right-hand side. You kind of distort it like that. And then you actually allow this quark to interact as well. So both of these guys now, we have a quark and antiquark, and they can interact. So I can draw some sort of a globe here. They can interact with a proton down here. And we're looking at the forward scattering amplitude. So the outgoing proton has the same momentum as the incoming proton. The incoming photon has the same momentum as the outgoing photon. So the picture is like that. So if you wish, I just said that topologically the diagram is the same, but these guys are far, far apart. So if I want to imagine the time ordering in this diagram, then this splitting happens before the interaction with a proton. If I go along the light cone, along the x minus light cone, the photon came along. Okay? Yeah.
Why does the color dipole intact with the proton, because the proton from the outside is also color neutral, right?
Right. So if it's a very good question. So if the color dipole was really zero size, it would carry zero color charge and it wouldn't interact with the proton. And this is a phenomenon known as color transparency. Zero size dipoles should interact very weakly with a proton. But because most of the time this dipole has a non-zero size, you have interaction. So the quark and antiquark try to screen each other, but because they're separated, they don't screen each other completely. Right, so color neutral objects can interact, right? Like a pion can interact with a proton. A pion also is approximately a color dipole if you just look at the valence quarks, right? So valence quark and antiquark, like UUR, right, and they interact with the proton. There's an effort to screen because it's color neutral object and all that, but interaction is not there. Okay, so but this is all moving us in the right direction. Let me erase it poorly.
Sorry.
Yeah.
So I have a question. What do you compile the fact that at high energy state of the calculation becomes weaker and weaker? The dipole, then I would think that the interaction is less standard knockout.
No, that's not entirely true. It's not so much with the coupling constant. So that's a good question. Let me try answering it. Let me show a slide. Hopefully it's not a crime. Yes. Let me maybe just show a slide in the interest of oops. So maybe what you're asking is the following. So this is the comparison of a dipole interaction and the knockout process. You may say that if the coupling is weak, right, you're saying, well, there should be some gluon exchanges maybe here, and then brings in at least an extra alpha S. But the point is that at small x, this diagram has 1/x enhancement compared to the knockout. Was that your question? Okay, because there were several interpretations I could see. So that's kind of it. If you're at low x, I mean, we're miles away from the future EIC side, right? If EIC probes x of 10 to the minus 3, 10 to the minus 4, right? That's 1/x is an enhancement by a factor of 1,000, 10,000. Alpha S on a good day is 0.1, right? And most of the time it's a bit larger than that. So you see that this is really not an enhancement factor, not a suppression factor, rather it's more of an enhancement factor. So it's just you restructure your operator. So if you use the OPE, you restructure your OPE differently. You talk about long-lived quarks and anti-quark lines rather than PDFs. In the end, it could be connected, but this is sort of a different way of expanding things. Okay. All right. So if we wrote this, so let's do it. This is the picture on the slide as well. We have a quark antiquark pair interacting with the proton, and the proton I'm just going to draw like this, and sometimes refer to it as a shock wave. Hopefully, it's not terribly shocking. Really, what we have is what I'm not drawing here is the transverse directions. Remember, this is a two-dimensional reduction of a four-dimensional picture. So the proton has quite an extent in the transverse direction as well, right? It's about a couple of Fermis in diameter in all directions, right? And it's coming straight at the dipole. The dipole comes towards it, right? So you can think of it. So this is a proton. Yeah. Well, proton about 2 Fermis size coming out of the blackboard at us, and the dipole, you'll see in a few minutes that the dipole size is roughly 1/q, or q is your photon virtuality. If q is perturbatively large, say a couple of GeV, right, that gives you some fraction like 0.2, 0.1 Fermi. So the dipole is much smaller than the proton. So this is the scattering, the small dipole is scattering on a big proton. And that's maybe part of the terminology. The proton appears like a shock wave to the dipole, right? It's also Lorentz contracted, so it's very thin. It's like a pancake coming at us. We're plowing through it with a dipole. Yeah. Okay. So as often happens in QCD, having time scale separation is very important, right? We see there's a long time, and I keep drawing it, but that was the argument there over there. We have a long time for the virtual photon to fluctuate into the quark anti-quark pair. And then the quark anti-quark pair interacts with the proton, and then we have a long time for the quark anti-quark pair to recombine back into the virtual photon. So again, we can separate those splitting and merger from the QCD interaction, and we can write the cross section for photon-proton scattering as a convolution. Okay, so here you should kind of trust me a little bit, right? It's always dangerous when they tell you to trust you, to trust somebody. But one could argue, I don't have the time to go into detail, but you have this Lorentz contracted proton, like I said, and we have the dipole plowing through the proton. The interaction may be strong, but the interaction is not strong enough to knock the quark and anti-quark significantly away from their path. Remember, this is a quark and anti-quark moving with a large minus momentum, right? The photon has a large minus momentum. They're going along the light cone with a large minus momentum. Sure, there is some momentum transfer that's possible between the proton and the QQ bar pair, but not enough to change this dipole, the size of this dipole. So if it was x perp before the interaction, it's approximately x perp after the interaction. So we integrate over all x perp. All pi is just a phase factor. We're also going to work in some, as you can see from this x perp, I want to work in the transverse position space, but I'm going to work in the longitudinal momentum space. So if this quark has momentum k, this anti-quark has momentum q minus k, and I define c as k minus over q minus, a fraction of the photon's momentum carried, say, by the quark. And then I also have to integrate over all z's. And trust me again, the proper phase space factor is dz over z1 minus z, integrated from 0 to 1. Then you have a light cone wave function for the virtual photon to split into QQ bar pair. I'll comment on this in a second. It depends on the size of the dipole and on z. And we have this light cone wave function here, and we have a light cone wave function conjugate here of the same dipole size. And the fraction z also doesn't change. So if this quark carries fraction z of the momentum, it remains z here, and the anti-quark still carries one of this on the other side of the shock wave. Sorry, and then we have the amplitude, the cross section, if you wish, for this QQ bar dipole, say to interact with a nucleon or a nucleus, which is a function of the size of the dipole x perp and center of mass energy S. So psi is a light cone wave function for gamma star to go into QQ bar. How many of you have not seen light cone wave functions? One. About I almost have 12. Okay, so for us, yeah, for me it's a challenge, yeah. But for us, it's a calculational tool. So what we just let me just think what I can say. So maybe so really we just want to calculate the Feynman diagram, right? So imagine you want to calculate the Feynman diagram where you have this dipole interacting maybe by exchanging gluons with a proton down here, right? This is like one of the lowest order non-trivial contribution to this short wave that you can imagine, right? So you can calculate this Feynman diagram, and so sorry, this I'm just trying to say that there's no vertex here. There's a vertex up here, there's a vertex up there. It's not like I have a disconnected view of Feynman. You can calculate it in any way you want. You can just calculate it as you would calculate any Feynman diagram. But if you want to have the separation of a QED process and QCD process, it's kind of convenient to assemble this part of the diagram into the wave function, and that part of the diagram will be the wave function conjugate. What's a wave function? Well, if I have a state, right, it's just like in quantum mechanics. I understand in a typical QFT class, people don't usually talk about wave functions so much, but the definition is almost the same. So suppose I have a state of field theory and I overlap it with some single particle state K. What is this? Well, in quantum mechanics, we would usually call it wave function. Huh? Yeah, it's just a wave function of a single particle wave function, right? If I take an overlap of my, remember, the state of field theory does not have a fixed number of particles, right? It's not a state in quantum mechanics. Number of particles changes all the time. If you don't believe me, open the, don't open. Look at the cover of Peskin and Schroeder. I have to open it. Right? You might have a, like if I have an electron may fluctuate into an electron and a photon, right? So that's two particles. So I take the same electron state, I overlap it with two different single particle states. Oh, I'm going to get a two particle wave function, K1, K2, etc. Right? So in fact, field theory is full of wave functions. We just don't usually talk about them unless you do these type of high energy QCD calculation. So what I mean by a wave function here is I have my virtual photon state, and specifically, so diagrammatically, that means I'm looking at a specific particle content in my quantum field theory state. So the state known as a photon, virtual photon, is either a bare photon, right? Or it's a bare photon which fluctuates in the quark antiquark pair, right? Or it's a bare photon which, okay, sorry, I'm going to erase this, but I think we have used this diagram already, this sketch quite extensively. It may also be a bare photon which fluctuated into a PQ bar pair and back onto itself. It could be higher Fock states. Remember the word Fock states in your QFT class, right? So those are different Fock states. We can have PQ bar state and a gluon, for instance. Who knew, right? The photon has gluons, etc. Right? So this is the photon state, and we are specifically interested in the photon fluctuating into QQ bar. So we need this component, which we single out by we work in a minus along the minus light one. So we have a quark and antiquark with momenta K and Q minus K. So we have a single quark state, which is defined by K minus and K perp, and an antiquark state, which has Q minus minus K minus and Q perp minus K perp momenta. And all of this will overlap with a photon state, and that's a wave function psi of K minus K perp and Q minus minus K minus Q perp minus K perp. Okay. Does it make sense at this level? I understand I'm not really calculating it, but we really only have. Yeah, Peter, 1 second. Let me ask Fred. Fred, how much time do I have?
We can flex a bit, yeah.
Okay, flex it. Okay, great. Peter.
Just one question. So, is it related then to the Parton distribution function of the photon?
It can be made related to the Parton distribution function of photon. The Parton distribution function is a single particle distribution. So if I want to make a PDF of the photon, and okay, it's a fairly advanced question. So if you guys are not with me on this answer, that's okay. So suppose this is my quark, and I want to tag on it, right? I want to have a distribution of quarks in the photon. In principle, that quark may not even be the original quark, right? It could be produced by some higher order. But I'm going to draw it like this just for simplicity. So strictly speaking, right, when you think of a PDF, you think of something like this, and all the other stuff, whatever you can think of, happens here, right? So yes, and then if you think of it, you say, oh, I know how to do it. I take an n particle wave function. So suppose I have n particles here. I have an n particles where I have one quark have momentum k minus and k curve, right? And then I have, I know, n minus one other particles. I take this wave function and I square it. Now, what's n minus one? N minus n is an arbitrary number, right? I have to sum over n from 0 to infinity. And of course, by the sum, I also mean I have to integrate over the phase spaces of all, or phase space of all these extra particles. Just when DIS we have, like, sometimes people write sum over x, which means not just sum over number of particles, but integrals of the phase space. So let me write here the phase space integrals. And then this is more like TMD, because this is for a fixed K curve. So it's a quark TMD in a, say, virtual photon state, right? So this is the quark TMD in the gamma star state. You guys have heard of TMDs by now, right? Just so it's a transverse momentum dependent distribution. It's really just gives us distribution of this quark as a function of K curve. I mean, K minus you can write as some fraction, say Z times Q minus, right? And then it will be also a function of Z, which is what variable X is. Okay, I can use the letter X, but we've used it before. So it will be a function of X and K curve squared. Well, in full generality, K curve vector. And then if you want a PDF, you just integrate the whole K curve. Now, when I do that, I don't have any gauge hints and all that. So presumably this definition works in some gauges where you can neglect the gauge hints, light can gauge the photon. So if the photon is moving in the minus direction, it's probably an A minus equals 0 gauge that you can get away with this, and then you may have gauge issues if you just work with the wave function. It's not okay. Okay, any other questions so far? Did I explain what the wave function is, or do you need more details? I mean, I can go on a technical hiatus, but then maybe we'll finish before lunch. But maybe a little bit of technicality is that, say, if I look at the Feynman diagram as written here, right? I have this antiquark propagator, right? You say, oh, but it's an antiquark. The single particle states are on mass shell. The antiquark is not on mass shell, right? But you can actually write a trick, do a trick where you can write the quark propagator as an on shell part and not on mass shell part. And then things get a little complicated in the end, but this is a one shell part that you need for the wave function. Let me maybe write something just to clarify what I mean. So if this is, you know what, let's just take the quark propagator. Let's change the interaction to something like this. By the way, all the diagrams need to be included, all possible connections. So let's say we have this quark propagator, and the quark propagator for massless quarks is I over K slash, or I K slash over K squared plus I epsilon. So quarks are massless. Then what I'm trying to say is K slash is K minus gamma plus, remember plus and minus notation, plus K plus gamma minus K curve gamma curve. What you see is, okay, these k plus, k minus, and k curve are completely arbitrary. They all have to be integrated over. But I'm going to do the following trick. I'm going to, instead of writing k plus, I'm going to write this own mass shell value, which is k curve squared over 2k minus gamma minus k curve gamma curve. And then I'm going to add the term, which is k minus k curve squared over 2k minus gamma minus, right? So I added and subtracted the Nagli structure of k curve squared over 2k minus, and you may wonder why I want to do it. Well, the reason I want to do it is that now, in the first line, I don't know if everyone can see this first line with all these pillars, I have a 4-vector k, which corresponds to what kind of quark? Has to do with this mass shell. Is it on or off mass shell? Yeah, this is a mass shell quark, right? Because by design, I think the plus momentum to be k curve squared over 2k minus, which is a mass shell value. For mass shell quark, we can write this first term as a sum of polarizations, u sigma of k, u bar sigma of k. Remember, you open any appendix of any of your favorite QFT textbooks, right? It has a formula that k slash for on-shell particles, and I'm dropping the mass, can be written as a sum of polarizations of u sigma, u bar sigma, all of k, right? So that's the first line. And the second line looks kind of ugly, but you realize that if you reduce it to the common denominator as k squared over 2k minus gamma minus, or with a plus sign, it's still ugly, but it has a meaning. It has k squared, which cancels this 1 over k squared. So let me erase a little bit here. This TMD discussion was more of a side remark. I think useful, but nonetheless, to go with a flow, we can write something like I k slash over k squared as I. I have the sum over polarizations, u sigma of k, u bar sigma of k, for the on-shell quark over k squared, plus I over 2k minus gamma minus. The last term k squared and 1 over k squared cancels. So here we see that we replaced the numerator of the quark propagator by the polarization sum, where we have u bar, u bar sigma, which we can pull into this vertex, and u sigma we can pull into that vertex. So now it looks like as if this quark line is outgoing, it comes with u bar, and this quark line is incoming, it comes with u, like in the QFT book. And then, of course, you say, oh, but there is this term, it's kind of funny, it doesn't have 1 over k squared. Yes, there are such terms, but trust me, they're not important here. And this is an example of a so-called instantaneous term. Instantaneous term. It will not be needed for our calculation, and let's just leave it at that. Okay.
Is it because it's higher order?
It's because in high energy scattering, it would not contribute. You see, the thing is that it comes with a gamma minus.
Well, okay.
And the vertex here will come with a gamma minus, and gamma minus squared is 0. So it's higher order in the sense that it will show up. It will show up if you calculate higher. So you can calculate corrections to this wave function.
I was thinking about the fact that the instantaneous vertex should have at least 2 powers of decoupling constant.
Which vertex should have?
The instantaneous vertex.
Oh yes, because right. So instantaneous. Okay, so instantaneous term. So I took a propagator now, right? I took a propagator and I wrote it as a polarization sum. Plus this instantaneous term. Instantaneous term is kind of denoted like this with a notch. It's instantaneous because it doesn't have 1 over k squared. If you Fourier transform it into position space, there's no propagation. That's why it's instantaneous. And it has 2 vertices because it's a propagator which connects 2 vertices, right? So here we had 2 vertices, one quark photon, one quark gluon. So here we could have, this photon and gluon as well, right? So that's what it would look like. An instantaneous term with those 2 vertices. Yes. Okay. All right. So this is all very good, but where is QCD in, right? So QCD, as I said, so if we more or less got what the light-cone wave function is, and trust me, this is well known in the expression. I don't have it in my slides. I don't think so, but you can find it in various references, including our book. What about the QQ bar gluon scattering cross section? Well, let's maybe the remainder of our meeting today, not meeting, remainder of this lecture, let's just try calculating, bless you, whoever sneezed, calculate the QQ bar scattering cross section, because that's where QCD is, right? So QCD is here, we came here to study QCD. So suppose I have a dipole, right? So now I have succeeded, maybe I waved my hands enough to remove this wave function here and remove this one here. So I only have, I'm left with a QQ bar dipole scattering on the proton. And I have diagrams like this. And like I said, we need to sum over all possible connections of the two gluons, the quark to the quark and anti-quark lines. All right, I think I have to erase something. Let's erase it here. The diagram, like maybe bunch them down here. So we have the diagrams like this, and diagram like that. Okay, we have four diagrams. Both lines connect to the anti-quark line, both lines connect to the quark line, and one connects to the quark line and the other one to the anti-quark line, vice versa. The order here is different.
I see.
Right?
I'll
It's a
go
left gluon that goes to the quark line, and it's a right gluon that goes to the quark line here. That's a good question. At some level, there's not much difference. Okay, so you do this calculation, and it's pretty straightforward if you've done any of these high energy calculations. Namely, suppose you have say, two quarks exchanging gluon at high energies. Let's say one quark is moving in the minus direction with a big P2 minus momentum, another quark is moving in the plus direction with a big P1 plus momentum. And suppose you exchange a gluon with momentum L. This is P2 plus L, this is P1 minus L. Very quickly, you realize, okay, this outgoing quark is on mass shell, so 0 is P2 plus L squared. Remember, P2 is has a huge minus component. All the other components fall by the wayside. We only keep P2 minus, so this is P2 minus L plus. Therefore, L plus is approximately 0. Photon carries no L plus moment. The outgoing quark is on mass shell down here as well. Here, P1 plus is a huge momentum. So this is approximately negative 2 P1 plus L minus. Therefore, L minus is approximately 0. Now you're beginning to worry, right? Does this gluon have any momentum components which are non-zero at all? Well, it does have curved momentum, right? So the propagator of the gluon, if we have some indices mu and mu, propagator of the gluon becomes L squared becomes just negative L curved squared, so we get I G mu over L curved squared. So this gluon propagates only in the transverse direction. Those of you from the SCAT community, you might have heard of Glauber gluons, right? This is a Glauber gluon. It doesn't propagate in a space in a TZ plane, in X plus or X minus directions, but it propagates only in the transverse direction. So it's an instantaneous gluon. It just jumps in the transverse direction. And okay, I have no choice but to erase this blob here. You can quickly argue, and I'm not going to have the time to do it carefully. I'm just going to write the answer. So you have these diagrams where, say, in the forward direction, you have momentum L going up, momentum L coming down. Each of these gluons is just a Glauber gluon gives you 1 over L perp squared. So when you put it all together, you get something proportional to, you have integral d to L perp, you have L perp squared squared. L perp, 1 over L perp squared comes from one propagator, we have two gluons, so we have two factors like this. And then if we have a dipole of a fixed size X perp, right? Then we have to do, remember, we're Fourier transforming in a transposition space. We're working in a transposition space. So this diagram actually a Fourier transforms, the Fourier factor is just 1. And so is the factor here. So altogether you get the factor of 2 minus e to the I L perp dot X perp minus e to the minus I L perp dot X perp. Okay. Does this kind of make sense? So I'm not going through the steps because we have no time, but so the Fourier factor here and here, right? Because the gluons connect the same, connect to the same antiquark line, but one has momentum flowing into it, another one has momentum flowing out of it. You can kind of think of it if this antiquark line was at some B perp, that this guy comes with e to the minus I B perp dot L perp. And here it comes with e to the plus I B perp dot L perp. And these factors cancel, and that's why it contributes 1 towards 2. Whereas here we have, say, e to the minus I B perp dot L perp, from this line being a B perp, and if this line is a B perp plus X perp, we have e to the I L perp dotted into B perp plus X perp. When these factors multiply each other, the B dependence cancels, but the X perp remains, and that gives me the Fourier factor. Does it make sense? Okay, well, you look at this integral and you see, okay, great, this is all wonderful, but and we can even do the Fourier transform, but it's infrared divergent, right? When L perp goes to 0, well, naively we have 1 over L perp to the 4th. The square brackets, if we expand them on small values of L perp, actually reduces only to logarithmic divergence, but nonetheless, we need to put some infrared cut of lambda, and we get something like X perp squared log 1 over X perp lambda if we do the integral. And in the end of the day, when that settles, the cross section for QQ bar scattering on the nucleon is going to be pi alpha s. So now I'm putting all the factors which I didn't want to, or didn't have the time to calculate. You get the pre-factor, okay? You get alpha s squared, that's clear, right? Each gluon gives you a power of alpha s. You have 2 gluons, so you get alpha s squared. Then you have color factors, CF and C pi. You know, nothing really, nothing complicated. Okay, so you say, great, we now have to calculate things. And by the way, what Peter was asking, that zero size dipole better not interact because the colors of quark and antiquark cancel. If X perp goes to 0, this goes to 0, right? So indeed, that's a sanity check that the calculation is correct. If we shrink the size of the dipole down to 0, then the interaction goes. Okay. Okay. So in the remaining 0 minutes, let's just make an outlook. Okay, you say everything is great, everything is Hidori, everything works. We know how to calculate dipole cross sections. From it, we can calculate cross sections for photon-proton interaction. Except there is a problem. If I ask myself or you guys, suppose instead of a single nucleon, we have a nucleus. So suppose now we have a nucleus down here. Now, for me, the nucleus is just a big bag of nucleons, and don't tell it to your nuclear structure colleagues, classmates, or whatnot. But say it's a large nucleus, and large nucleus has a lot of nucleons in it, obviously, and it has 8 nucleons. right? A is a mass number, which somehow, usually in our neck of the woods, we call it atomic number. So I'm going to be calling it the atomic number, but it's the total number of neutrons and protons. And then say the radius of the nucleus scales as a to what power? Does anyone know? Hmm?
One.
No, not one. What was it?
No, one over.
Further.
1/3, yes.
1/3.
1/3, yes, sorry. 1/3, right? Everybody is cool with that. Okay, so then let me just tell you a simple thing. So suppose I want to scale up my cross section for the case of a nucleus, right? You say, oh, big deal, sure. Okay, so about in the case of a nucleus, the lowest order, still at the lowest order in the coupling. It could be that the first nucleon interacts. I'm gonna write it kind of loose like this. These disconnected blue lines mean the sum of all four diagrams. Or I may have the second nucleon interact. Or I may have the third nucleon interact, the fourth nucleon interact, etc. Right? So all the way to the last nucleon. Okay. So then the cross section for four kinds of quark scattering on a nucleus is going to be, well, one can write something more complicated, but let me just write a simple formula that the cross section will scale is the number of nucleons you can find in a given impact parameter. So you have e to the 1/3 nucleons at a given impact parameter, right? Because the radius of the nucleus scales as e to the 1/3. If you imagine a dipole flying through the nucleus, at a given impact parameter, it encounters the number of nucleons roughly of the order of e to the 1/3. And then we have the cross section for QQ bar scattering on the nucleus. Okay, does this make sense? The hand-waving level, right? You just pick up a factor of e to the 1/3 because you have more nucleons to interact. So we're still assuming the interaction is weak. If they can interact, the dipole can interact with only one nucleon, but it could be any of those nucleons, right? So we just have like a numerical advantage, right? The interaction gets stronger because we have a lot of nucleons. A is large. So we assume that A is very, very, very large, and e to the 1/3 is kind of large. And don't ask me what large means, right? If A is 200, whether 6 is a large number, I would argue that 6 is a large number. But we can debate that. At one point, Whitman had a wonderful argument that 3 is a large number. I'm with him on that. Okay, so yeah. So we have a cross section which increases like this. Then there is a problem. The problem is okay. The problem is as follows. Let me define. So the cross section, say for a nucleon, we can write it as using optical theorem. Remember optical theorem, the cross section is equal twice what? Imaginary part of the foreign amplitude. Very good. You all know. It's pleasant to see so many people knowing optical theorem. When I teach quantum field theory back home, one or two students maybe in the room know that. So we're going to write the, we're going to define something called the dipole amplitude, dipole scattering amplitude, which is a function of dipole size, impact parameter, and energy. So imagine this is a dipole. It has size x curve. It is located distance b curve from the proton or nucleus it interacts with. And the scattering energy is S. And this is the imaginary part of the forward scattering amplitude F. And then we can write the cross-section length Again, here you can kind of trust me, but it's also intuitively clear. We integrate over all impact parameters, right? The cross section in general has an integral over all impact parameters times this imaginary part of the forward scattering amplitude, which depends on X curve, V curve, and S. And remember, that gives us a cross section which depends on X curve and S. Okay. So this is the dipole amplitude for scattering in a proton if this is a N, or a nucleus if this is a nucleus. So this blob down here could be a single nucleon, could be a full nucleus. Okay. There is, however, a unitarity argument. Maybe we'll bring it up already in the discussion time. Unitarity. So unitarity requires that N. So first of all, it's a cross section. So N better be greater than or equal to 0. But unitarity requires that it should be also limited by 1. Strictly speaking, by 2, but in high energy scattering by 1. So, and that's just a postulate that I'm making. Now, let's see what happens to our N, right? So we have this dipole amplitude N. We have the cross section. We want to construct the cross section for QQ bar dipole interaction. Let's see. So I'm just trying to reiterate this formula in a little bit more detail, but you're going to see that in fact it is qualitatively correct. You'll see what the problem is with this point. So the cross section at the given impact parameter scales as a to the 1/3 times the cross section on a single nucleus. We define something called T of B, the nuclear impact factor, or the nuclear profile function. Sorry, nuclear profile function. So T of B is going to be an integral over, say, the Z variable, the number density of the nucleons at the given V curve and Z positive. Okay, so this is the nuclear profile function. And loosely speaking, this is a singular scale that's a to the 1/3, right? Counts how many nucleons you have at the given input parameter, you integrate over all Z. It's kind of like probes the number density at the given input parameter in the nucleus by integrating over all these. So this statement being done more carefully is that statement right here. On the other hand, I can write the analog of this formula for the nucleus, right? Then it would be twice integral into the curve and the dipole amplitude for scattering on the nucleus of X curve, D curve, and energy. Comparing these two, we see that indeed the amount of space again. Can I erase? I don't want to write the result in the corner. So let me, I think this calculation can go. I'll leave the diagrams because I think they're good to keep them. So we see that twice times N is equal to T of B per sigma of QQ bar N. So the dipole amplitude of X per B perp and center of mass energy S is 1/2 T of B nuclear profile function times sigma QQ bar N, which means that this is 1/2 T of B perp pi alpha S squared CF over NC X perp squared log 1 over X perp 1. Okay. Let's call this leading order. So LO subscript means leading order because this is just due to a single exchange. Okay, now what am I worried about? So I'm going to erase this
A
down.
few more minutes probably.
Yes, this is I'm finishing. Yes. So let me just finish by giving you a worry. Remember, I said unitarity means that n should be less or equal to 1, right? Now, you have T of B. T of B curve scales as a to the 1/3, this number of nucleons given input parameters. It also has dimensions. Remember, rho is a number density of the nucleons. It's a number of nucleons per unit volume multiplied by the distance. So we get dimensions of 1 over area. So therefore, it has some dimension of 1 over area. We put some lambda of the order of lambda QCD squared, right? So it has dimensions of momentum squared. We see that Rn leading order scales as a to the 1/3 x perp squared lambda squared. Okay. Times some other factors. So here lies the problem. If I strictly speaking just take this dipole amplitude and plot it as a function of the size of the dipole, I'm going to get sort of a parabola-like behavior. It starts from 0, the origin, right? 0 size dipoles don't interact, but it shoots up and it never stops, right? It will eventually pass the unitarity bound of n smaller than 1. So it will violate unitarity. Now, without a to the 1/3, you could say, oh, big deal. It will violate unitarity when x perp is of the order of 1 over lambda. Things will go non-perturbative. All your gluon exchanges theory will not apply anymore. So you shouldn't worry about it. But that's where the nucleus comes in. If we have a large nucleus, violation of unitarity happens when that thing becomes order 1, right? So that means x perp here is 1 over lambda a to the 1/6. Okay, 1/6 is not as big as 1/3, but still a positive power. So for large enough a nucleus, sorry, minus 1/6. Right? For large enough a nucleus, this is still much smaller than 1 over lambda. So we may still be in the perturbative region, right? So the dipole is still perturbatively small, much smaller than a Fermi, but our interactions will already violate unitarity. That cannot be true, right? Our theory, our perturbation theory, QCD doesn't violate unitarity. QCD is a unitary theory. A perturbative implementation of QCD better not violate unitarity. So we have a problem. We violate unitarity in a region where the calculation is still perturbative. Okay, and this problem we're going to address and solve in the next lecture. Okay, so to recap, we have devised a new way of tackling deep elastic scattering at high energies. We changed, we went through a sort of a change of approach to it from the knockout process to a dipole proton interaction. And then we said, okay, very good, let's calculate dipole proton interaction. We'll calculate some, we found some cross section, which was fine. Then we tried scaling that up to a nucleus, and we found the violation of unitarity. So that's indeed an issue, and we'll deal with it later. And it's related, some of you might know, related to saturation physics and saturation effects, which will come in and actually unitarize this, this cross section. So indeed, we will not leave unitarity violated and unfixed. Questions? Sorry for running over, but
let's thank Yuri, and we'll have a discussion section this evening, so let me encourage you to do that. Also, I recommend his book with Levin, which is excellent, has a lot of this, and the slides are up there. So, and I think you're working on a movie, if I remember, movie deal, if I remember.
You didn't know that, am I?
Oh.
Saying?
Anyway, yeah, so let's go ahead and take a break and we'll start
sorry.
again. We'll start again at 1:30. And a quick announcement, today you can, if you want, you can trade your linens between 4 and 6 of the housing office. So if you don't have to, but if you want to, you can stop in there. And so let's pick up again at 1:30. Have a good lunch. Michael? And I'll lock this room again, so.
I don't have color. It's very cute.
That I knew, but.
And
We'll do assignments.
Yeah, but I also wanted to do some forms, but I don't know, you know, those forms, are you? Online here.